Unit 3, Number and Logic. Section 2, Logic and Reasoning. Chapter 1. We've already completed Chapter 4 on number, so now you're going to work on Chapter 1, which is Logical Reasoning. At the conclusion of this section, you will be able to develop number sense and logical reasoning. You're going to analyze and prove conjectures using inductive and deductive reasoning to solve problems, and analyze puzzles and games that involve spatial reasoning using problem-solving strategies. In Math 10C, the concept of... Oops. I guess I need to change that part. Oh well. You haven't done anything that has to do with this kind of material before, so this will be pretty new for you, but it is an important part of what you're going to be learning, for real life. Okay, here's the checklist of requirements to complete this section. There's a pre-assessment, Part 1, Making Conjectures, Inductive Reasoning, Part 2, Exploring the Validity of Conjectures, 3, Using Reasoning to find a counterexample to a conjecture, Part 4 is Proving Conjectures, Deductive Reasoning, Proofs that are not valid is Part 5, Reasoning to solve problems is Part 6, and Analyzing puzzles and games is Part 7. There'll be a review in the form of a formative assessment, a curriculum review, a quiz, both of those are your minor summatives, and then there'll be an exam on number and logical reasoning, so that's chapters 4 and 1. Alright, here's a little cartoon. Penguins are black and white. Some old TV shows are black and white. Therefore, some penguins are old TV shows. Logic isn't another thing that penguins aren't very good at. Okay. So, as I mentioned on the first page, there's a lot of jobs that require you to use reasoning, both inductive and deductive. Now, you probably don't know what those two words mean yet, inductive and deductive, but you will by the time you're done this chapter. Some of those jobs are in the categories of management, sales, construction, professional, administrative, installation, transportation, service, farming, and production. So, those are 10 broad categories, 114 jobs. That's quite a few. All right, let's find out what all this has to do with. Example 1. Georgia, a fabric artist, has been patterning with equilateral triangles. Consider Georgia's conjecture about the following pattern. Okay, so equilateral just means triangles that have all three sides the same length and all three angles the same size. Okay, so in figure 1, we have one triangle. Figure 2, 1, 2, 3, 4 triangles. And again, we're looking at ones that are the same size, okay? So here's George's conjecture. She thinks that figure 10 in this pattern will have 100 triangles. All these triangles will be congruent, so the same size and shape and measure as the triangle in figure 1. Okay, so let's fill in our table. So 1 has 1 triangle. 2 we figured had 4. 3 has 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 triangles. So what do you notice about the data in the table? 1, 4, 9. What kind of numbers are those? Looks like they're perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9. Extend the pattern for 2 more figures. So figure 4 and 5. Okay, and what do you think? Well, 4 squared should be 16, and 5 squared should be 25. And if you want to draw the triangles, you can just add some more rows. We had 1, 2, 3, 4, 5, 6, 7 more triangles for figure 4. 7 and 9 makes 16, so we're right. And again, you could add another row if you wanted to, and do the same for that. I'm probably imagining that you're going to end up with 9 more triangles. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, 9 and 16 makes 25. Okay. What numeric pattern do you see in the table? So, they are perfect squares. You can also say that they go up by the consecutive odd numbers. So this goes up by 3, this goes up by 5, this goes up by 7, this goes up by 9, so on and so forth. Okay? So, you can say increases by the square of the figure number. Okay, so is Georgia's conjecture correct? She thinks that figure 10 in this pattern will have 100 triangles. Well, 10 squared is equal to 100, so it looks like Georgia's conjecture is pretty good. So inductive reasoning is when a pattern is observed in a set of data, and the pattern is then used to make a generalization or educated guess about the data. The generalization is called a conjecture. When you're asked to use inductive reasoning in order to make a conjecture or generalization about some pattern, take the following steps. Examine a number of cases that are typical of the situation. In that last example, we looked at 5 different figures, and the pattern held the entire time. See if you can recognize some kind of pattern in the data, and then make a conclusion or conjecture based on the pattern. What conjecture could you make for the following situation? Eli has lunch at the same deli every day for a week. Each day, the special of the day has included fries. Based on this, what can Eli conclude about his next visit to the deli? Well, he can conclude that nothing has changed, and that the special of the day will include fries. Okay. Part B. Justin arrives at his first block class at 8:10 a.m. Every day for the past 3 days, his teacher has arrived between 8:12 and 8:14 a.m., and class starts at 8:15. Therefore, he can conclude that tomorrow his block 1 teacher, well, the same thing that's happened in the past 3 days, will arrive between 8:12 and 8:14 a.m. Okay, isn't this fun so far? It's kind of a weird and different type of math, but it's still math, don't worry. Number 2, use inductive reasoning to make a conjecture about the following situations. Add 2 odd numbers and note the result. Repeat the experiment several times. What conclusion can you make? Okay, so let's add a couple of odd numbers. Let's go 7 and 9. That makes 16. Okay, let's go 23 and 41. And that would give me 64. Okay, let's add 251 and 749. Okay, that should make 1,000. And we'll do one more. Remember, for it to be an odd number, just the last digit has to be odd. So something like 6, 4, and 3. I'll make that 1643. And 8, 4, 2, 1. I'll make that 5. Okay, 8425. Okay, because I haven't used the 5 yet. Good, alrighty, so let's add that up. That would give us 8. 2 and 4 makes 6. 8 makes 10, carry the 1. That makes another 10. I need to, whoops, give myself a little more space here. Come on, eraser. So 10,068. Okay, every single time I have added 2 odd numbers, if you'll notice 16, 64, 1,000, 1,000, 10,068, my sum is an even number. And again, at any time, you can pause the video, try this yourself before I give you the answers. So, up to you. Okay, number 2B. Multiply an even number by an odd number and note the result. Repeat the experiment several times. What conjecture can you make? Okay, so 2 times 3. Okay, and that's 6. And we'll go 12 times 5. That makes 60. And what else? 14 times 7. I think that's 98. Okay, and let's go something times 9. 10 times 9. Try not to make my brain work too hard here. There's 90. Okay, and we'll go 10,000 times 1. Okay, so there's 5 examples where I multiply an even number by an odd number. If you'll notice, the product in each case is also an even number. So, the product, which of course is the answer when you multiply, of an even number with an odd number is an even number. That's my conjecture. Okay, great. A few more examples, and again, feel free to try these on your own. Now, for these ones, you might need a protractor, but you should be able to take a look at some of the pictures I'm going to draw and see if you can come up with something. Okay, so scalene triangles. Scalene means all 3 sides are different. So, I'll make that really long, and then that guy, and like that guy. Okay, so we want to measure each of the angles on each of the sides. So the smallest angle, of course, would be this one right here. And guess what? If you take a look at the side opposite it, okay, this is the shortest side here. Okay? So smallest angle, shortest side. Let's see if we can do a right scalene here. Okay, and again, we know the right angle. And so this, of course, is the hypotenuse, which is the longest side on any right triangle. This is my smallest angle, and if you'll notice over here, that is my shortest side. So, let's draw an acute scalene. Okay, and this looks like my smallest angle, and over here would be my smallest side. So, the conjecture I'm going to make is the shortest side is opposite the smallest angle. Okay, good. And last but not least, D. Construct several pairs of intersecting lines. Measure the pairs of vertically opposite angles. What conjecture can you make? Okay, so intersecting lines. There we are. Okay, now vertically opposite angles are this guy here and this guy here. Or this one here and this one here. Make a little smiley face. Okay, what conjecture can you make? Well, if I look at those two, what do you think? If you look at those two, what do you think? Let's try and make them a little more pronounced. Okay, and this is opposite to this. This one's opposite to that. Okay, we can even make them at right angles to each other. Okay, so there we go. And of course, what do I notice about these two vertically opposite angles? Okay, good. So I'm going to make the conjecture that vertically opposite angles are equal. Now, it seems like, oh, we can just say whatever we want, but you really should be basing your conjectures on a few pieces of data, at least 3. Okay, some key ideas for this section. Inductive reasoning uses a pattern, whether geometric, shapes, algebraic, letters, or arithmetic, numbers, to make a conjecture or generalization about future events in the pattern. Inductive reasoning does not always prove something to be true. More support for a conjecture strengthens the conjecture, but it does not prove it. So the key idea behind inductive is you have to have lots of data, and it does not prove it. It just shows you that the pattern is, a pattern. All right. Page 12. 2, 3, 5, 9, 11, and 12. Show your teacher when you're finished this formative assessment.